Hi everyone. This lecture is going to discuss the Fresnel equations in electromagnetism. Now, the general case of working out the reflected and transmitted components of electromagnetic waves at a boundary between two materials is embodied in these so-called Fresnel equations. However, it is more complicated than determining the reflection and transmission coefficients for string waves, for example, because electromagnetic waves have two field components, the electric field and the magnetic field, with polarization, meaning they are vectors, they have a direction for these fields. So it is more complicated than what was done to work out the part of the wave that reflects on the boundary, say, for a rope going from, say, one density to the next. So what are we going to do? Well, we're going to solve this by applying the electromagnetic wave boundary conditions, or at least boundary conditions for electromagnetic waves, and Maxwell's equations. And one result of these lectures, and this result, is that we'll be able to explain where Brewster's law is coming from quantitatively. Okay, before we get started, let's summarize and review Maxwell's equations, both its integral and differential forms. So the first one listed here is Gauss's law for the electric field, and that can be written as a surface integral, meaning the flux enclosed by a surface is equal to the charge enclosed by that surface divided by the permittivity of free space, epsilon naught. The differential form, where you use the divergence theorem, is that the divergence of the electric field is equal to the charge density divided by epsilon naught. Now, the same thing for the magnetic field. Well, there are no magnetic monopoles, so the flux over a closed surface is always zero, and the differential form is that the divergence of the magnetic field is always zero. Now, for Faraday's law of induction, we had this line integral E dot ds around, say, some enclosed loop, and that equaled the negative of the time derivative of the enclosed flux through the surface described by that loop, B dot dA, the magnetic flux. Using Stokes' theorem from vector calculus, we can say that the curl of the electric field, del cross E, is equal to the negative time derivative of the magnetic field. And finally, Ampere's law combined with Maxwell's law of induction is that the symmetric version of that previous Faraday's law is that the line integral of B dot ds is equal to the flux through the surface enclosed by that line integral, with the time derivative taken of that, times mu naught epsilon naught, and then plus any enclosed current times mu naught, the permeability of free space described by that loop. The differential form is that the curl of the magnetic field B is equal to mu naught epsilon naught times the time derivative of E plus mu naught times any current density in that region. So that's just a brief summary of Maxwell's equations. However, I want to mention an alternate form of these equations when you're describing the electric and magnetic fields in matter can be listed this way. We can introduce a displacement field D, where the divergence of D equals the charge density of free charges. Matter has both charges embedded and fixed in the solid, if it's a solid, from, say, the electrons and protons there. But the free charges, the ones that are free to move, give rise to what is known as a displacement field. So this displacement field equals the electric field times a permittivity constant in front of an epsilon. And rho free is the free electric charge density in this dielectric material. We still have the divergence of B, the magnetic field, is zero. The curl of E is also still minus dB dt, the negative time derivative of this magnetic field. And then we can introduce the H field, where the curl of H is equal to the time derivative of the displacement field D of the electric, from the electric field side, plus any free current densities. So J free is the free current density of charges that are freely moving. And what is the H field defined as? That's related to the magnetic field divided by the permeability of free space minus any magnetization that occurs in that material. So M, vector M, is the material magnetization. For non-ferromagnetic materials, that magnetization is basically proportional to the applied B field. And so we can write that the H field is just the B field over mu, which is the permeability of that material. If it were free space, mu would be mu naught, and epsilon would be epsilon naught for the displacement field in free space. So that's just introducing the alternate form of Maxwell's equations in matter. And I mention that because we want to understand the boundary conditions that come from the laws of electromagnetism. So for electromagnetic waves traversing from one material to another, the following boundary conditions apply for the components of the field parallel to the boundary surface. Basically, the components of the electric field parallel to the surface must be continuous. Likewise, the parallel components of the H field, which is related to the magnetic field by 1 over mu, is also continuous. For components that are perpendicular or normal to the boundary surface, we have that the perpendicular component of the displacement field, which equals epsilon, the permittivity of the material times the perpendicular component of the electric field, must be continuous. And we have that the perpendicular component of the magnetic field B pointing through the surface, through the boundary of the two surfaces, is also continuous. So I'm not going to discuss how these were obtained in electromagnetism, but just to mention that these are the boundary conditions that come across. Okay, so let's address the topic of this lecture, which is we want to solve for the reflection and transmission of electromagnetic waves on the boundary between two dielectrics. So I show here on the right a diagram here. We have an incoming wave in a material with index refraction n1. It's reaching a surface with another material with an index refraction n2. My incoming wave is described by its wave vector ki. I use I for the incident direction. So ki is coming in. And then the wave, when it reaches this boundary, and assuming the second material is transparent, even though it has a different index refraction, some part of the wave will reflect off, and some part will be transmitted into that medium. The incident angle for the incoming wave is theta I from the normal to the surface, or the boundary. The reflected angle theta r is the same angle from the normal to the surface. For the reflected wave, of course, those two have to be equal by the law of reflection. And we'll let theta t be the angle of the transmitted wave into the new material with index refraction n2. So basically, to sum up, when an EM wave is incident on the boundary between two materials with different indices of refraction, some part of the wave reflects and part is transmitted through the surface. All right, so now let's consider an incident EM wave with the electric field aligned in the plane defined by the incident and reflected waves. So here I have the incident wave and the reflected wave. They're basically in the plane of your screen or your page. And so we're going to let the electric field be in the same plane. So parallel to the plane defined by Ki and Kr. And by the way, the transmitted wave has to be in the same plane as well. Now I've drawn EI, the component of the incident electric field, obviously at a certain point in time, and the same thing for the reflected wave here. And notice that it is perpendicular to the direction of motion as it must be for a traveling electromagnetic wave. Right? So there's a perpendicular angle there. Okay, mathematically we can describe these traveling waves with the complex exponential notation. So my incident wave has some incident amplitude and direction. And then it's e to the I ki dot r, where ki and r are vectors, the incident wave vector and basically the position vector r, minus omega t, or minus I omega t when you multiply into the binomial. So that's the oscillating piece. Reflected wave is described similarly, except the wave vector changes to the reflected wave vector kr. For the transmitted wave, again, something similar. Of course, the amplitude's different. It's E0t versus E0r for the reflected wave and E0i for the incident wave. And it has a different wave vector for the transmitted wave kt, so it's kt.r inside the argument to the complex exponential. All right, so we just discussed a moment ago the boundary conditions, and one of them is that the electric field parallel to the surface that defines the boundary between two media must be continuous. Now, that is not this component of the electric field which is parallel to the plane defined by Ki and Kr. It's that component parallel to the surface, which means it's going in and out of the screen, not in the plane of the screen. So to do that, I'm going to have to project EI, ER, and ET into the plane that is parallel to this surface here. So I need to project EI along this horizontal direction. So I can do so if I just draw, for example, a line across. I basically have to project EI onto that purple horizontal line, and so I need to solve for some angles. I know that theta I is the incident angle. That's this angle here. That means that angle at the top left of this triangle I've defined with the magenta line would be 90 degrees minus theta I, because this one's 90, of course, and I can draw that perpendicular there. That means the one up here is equal to theta I as well. So this angle up here is theta I. So I just need to take the cosine of that angle to project EI onto this horizontal direction. So that's what I've done here from that boundary condition. And I need to do the same thing for the reflected wave. But as you can see, as it's going out, and it must be perpendicular to its outgoing direction, it kind of points in the negative x direction if x is this horizontal direction. So I'm going to do the same thing projected on to that axis. It's still going to be another cosine, but it does flip sign because it's going to be pointing in the opposite direction than the incident wave was. So I have minus E0r cosine of theta r. For the transmitted wave coming out here, that looks like it's going to project, and I take the perpendicular component here, sorry, the component parallel to the surface. When I project onto that direction, that's going to be in the positive direction, and you can work out that that'll be also a cosine, in of this case, the transmitted angle theta t. Now, we have the law of reflection, so that means the incident angle equals the reflected angle, theta I equals theta r, those are here in the left. So I can just set those equal to theta I, and then divide everything by cos theta I, and I just have E0I minus E0r is E0t. These are the magnitudes of those incident, reflected, and transmitted waves, times cos theta t, again from that boundary condition, divided by cos theta I, because I divided it out everywhere here. And so that'll define equation 1, which we'll come back to in a moment. And just to highlight again, that negative sign came from the fact that the reflected wave was pointing in the opposite direction. Now, I also had this other boundary condition mentioned earlier about the component of the H field parallel to the surface. That is basically means that the parallel component of the magnetic field B divided by the permeability mu is continuous. But if mu is a constant essentially from n1 to n2, meaning it's not magnetic, or at least the deviation from that of free space is very small, we can basically take it to be constant, that would just mean that the parallel component of the magnetic field is also continuous across this boundary. Now, I didn't draw here the magnetic field yet, so let's go ahead and do that. So I've drawn it here in green, the incident magnetic field, the reflected magnetic field, and the transmitted magnetic field. Remember, again, it must also still be perpendicular to the direction of motion of the wave, and we know it has to be perpendicular to the electric field as well. And E cross B, that vector cross product, points in the direction of the wave direction k. So you can do a right-hand rule, E cross B, E cross with B pointing out of the screen would be a wave pointing down and to the right, like the incident angle for this incident wave. Likewise, for the reflected component of the magnetic field, E cross B, he has to point out the page here on the right side, and E cross B would point up and to the right. And likewise for the transmitted wave. So B is always pointing out of the screen in this case, And in fact, we would see that it's completely parallel to the surface of the boundary defining those two media. So that makes things a little bit easier. No projections with cosine theta. The other thing to note is E and B are related for electromagnetic waves, right? E over B is equal to omega over K, but that's also the speed of the wave. And the speed of the wave is the speed in vacuum, the speed of light c, divided by the index refraction n. So just rewriting this by multiplying through by b naught, we have that b naught, and then if I flip over and divide by c over n, is e naught times n over c. So I have the relationship between b naught and e naught. So the continuity of the parallel component of the magnetic field, B0I plus B0R has to equal B0T. These are the amplitudes of the incident, reflected, and transmitted magnetic fields. Doing this substitution here, I just know that N1 times E0I plus N1 times E0R has to equal N2 E0T, just doing this substitution. It's the same index refraction for the incident reflected wave because they're on the same side of the boundary. So I can just divide those by N1 everywhere to cancel out on the left side, and I have that the amplitudes E0I plus E0R, the incident and reflected wave electric field components, equals the magnitude of the transmitted wave amplitude times the ratio N2 over N1. And we'll call this equation 2. Okay, so 1 was this one in blue here in the middle of the page, and 2 is the one down below. And I'll repeat those on the next slide. So we're going to try to solve for the reflection coefficient ratio, which is just the magnitude or the amplitude of the reflected electric field over the incident electric field. And that will define our reflection coefficient for the case when the electric field is parallel to the plane divided by Ki and Kr. Again, that's not quite the same thing. It's not the same as parallel to the surface. It just means parallel to this plane of the diagram. So our two equations, again from the last slide, were that E0I minus E0R equals E0T times cos theta T over cos theta I. And E0I plus E0R was E0T times the ratio N2 over N1. So we had that from before. So what can we do? Let's just do a little bit of algebra. Let's add these two waves. Sorry, these two equations, 1 and 2. If I do that, I'm going to get twice E0I, and the E0R term cancels out. Then I have E0T, and then I have N times N2 over N1 plus cos theta 2 over cos theta I when I add them together. So that's adding them. I could subtract instead. I'm going to subtract the first one from the second one. So 2 minus 1. So that will cancel the E0I piece. Then I'll have E0R minus the negative E0R, which means just twice E0R. Then I have E0T times, and then I'll have again N2 over N1, but now minus cos theta T over cos theta I. So this is another relationship here. So if I wanted to find this reflection coefficient for this case where the electric field is parallel to the plane of the reflection, I need the ratio of E0R over E0I. I kind of see that right here. If I divide the subtracted equation by the added equation, I have 2 E0R over 2 E0I. The 2's will cancel, and I'll have just E0R over E0I. So that just means I need to take a ratio of this piece here divided by the other piece there. And so that's what I've written here. The E0T will cancel, right, when I take that ratio. So I just have N2 over N1 minus cos theta T over cos theta I. That's this term. Over almost the same thing, N2 over N1 plus cos theta T over cos theta I. All right. But what we're going to do now is, so in principle you're done if you know these, the transmitted angle of the wave as well as the incident angle, but we can put this in a slightly more informative form by just doing a bit of algebra and some trig identities. And also we can rewrite for the transmitted angle. So let's go ahead and use Snell's law. Right? Snell's law says N1 sine theta I equals N2 sine theta T, going from the incident medium to the transmitted one. And so I can solve for n2 being just n1 sine theta I over sine theta t. So n2 over n1 is just going to be this ratio of sines. So I can take this ratio of sines and plug them in here and here, right? So that's what I'm going to do. I'm plugging in that ratio of sines to be n2 over n1. And so I have that sine theta I over sine theta t, both numerator and denominator, and then the same terms that were in the numerator and denominator, minus cos theta t over cos theta I, plus cos theta t divided by cos theta I. Okay, what I can do one more time now, because I don't like the terms that are in the denominators inside both the numerator and denominator of the bigger expression, so I can go ahead and multiply by, what do I want to multiply by? I want to times this by sine theta t to cancel the one in denominator there. And I also want to times by cos theta I, right? So if I multiply through top numerator and denominator of this expression for r parallel, I will cancel those denominators within the numerator and denominator of r parallel, but I will get an extra term. So I'll get the sine theta I times cos theta I here, and then over here I cancel the theta I and I have sine theta t cos theta t. Likewise in the denominator it's the same thing, but the minus turns into a plus. All right, so we're just kind of doing some gymnastics with the trig functions, and we'll do a few more. So that's what we left with from the last slide. That's the equation for r parallel. Let's do a few more trig identities, because here we have kind of products of sines and cosines. One trig identity is a double angle identity that sine of 2 alpha is twice the sine of alpha times the cosine of alpha, where alpha is some angle. Well, here I see a bunch of sine cosines. Sine cos, sine cos, sine cos, sine cos. So substituting in what alpha is, either being theta I or theta t, I can replace them with the sum of twice theta I or theta t in this trig identity. So if I do that, this sine I cos theta I becomes 2 of sine of 2 theta I, or 1/2 I should say, 1/2. There's a 1/2 that's out here in front of each of these things, but that's going to cancel out basically when I take the ratio. So all I've done is replace these products of sine cosines with the double angle formula for sine. Then I'll use a few more identities. One is that the difference of sine alpha minus sine beta is twice the cosine of alpha plus beta over 2 times sine of alpha minus beta over 2, and the sum of sine alpha plus sine beta is twice sine of alpha plus beta over 2 times cosine of alpha minus beta over 2. So I can use these identities as well, and this will let me replace this difference in sines, or this sum in sines, in terms of these products of cosines and sines. So we're slowly wheedling away the original r parallel expression down to some basically just ratio of single trigonometric functions if we can. So I've got the difference of sine of 2 theta I minus sine of 2 theta t. That's my alpha and beta. So I could add those together, and I'll have 2 times cosine of theta I, 2 theta I plus theta t over 2, which just means theta I plus theta t over, not over 2. And then I have this other sine term, which is alpha minus beta, so that'll be 2 theta I minus 2 theta t over 2, so I'll be just theta I minus theta t. So that's how I've replaced the numerator of my r parallel expression. The denominator is basically the same thing, but I have to use this alternate form with the minus becoming a plus. That's just going to swap some sines and cosines. So I'll have sine of 2 theta I plus 2 theta t over 2, so that's just theta I plus theta t with the sine of that. And then the cosine piece is the difference, theta I minus theta t, the 2 canceled, and that's a cosine. Phew, so there we go on that. And if we look at this, I see here that I have a sine of theta I minus theta t over cosine of theta I minus theta t. That's sine over cosine. That's just a definition of a tangent of theta I minus theta t. And over here I have sine of theta I over theta t in the denominator for our parallel, divided by, in the numerator, cos theta I plus cos theta t. So that's a tangent in the denominator, tangent of theta I plus theta t. So that's it. We worked out the expression we wanted to find, which is that the reflected coefficient, when the electric field is parallel to this plane of the reflection, meaning in the same plane defined by ki and kr, this is how that reflection coefficient depends on theta I and theta t. And so this represents one of four so-called Fresnel equations. And so we worked out our parallel. We can similarly work out when the electric field is not parallel to this plane of the reflection, but rather perpendicular to it. That would be parallel to the surface, for example. So that would be r perp. And also we could work out for the transmitted wave. Don't worry, we're not going to do all of those calculations. I just showed you one for the r parallel. We're talking about this reflected wave piece here when E is parallel to the plane of the reflection. And what I'd like to point out is because of this tangent in the denominator for the expression, tangent of theta I plus theta t, if theta I plus theta t become 90 degrees, I have the tangent of 90 degrees. That's equivalent to the sine of 90 degrees over the cosine of 90 degrees. That's 1 over 0, which becomes infinite, of course. So the tangent when this approaches 90 degrees becomes infinite. So infinite in the denominator for my expression for our parallel means that our parallel is going to 0. So our parallel goes to 0, which means that polarization component vanishes. When theta I, which by the way equals theta r, when theta I plus theta t equal 90 degrees, then there is no reflected component of this electromagnetic wave. There's no reflection when the polarization of that electromagnetic wave is in that plane of the reflection. It's all transmitted. So very interesting. That is basically Brewster's law, where only now one polarization component remains, and that's the one not parallel to this reflection plane, but the one perpendicular to it. So that was the main goal, but we can explore this a little bit more carefully, as well as discuss those other Fresnel equations. So I'll move on to the next slide. So here was our expression for our parallel, the tangent of the difference theta I minus theta t over the sum tangent theta I plus theta t. And now this is just a plot shown here. This is a plot versus the incident angle. So I'll write versus theta I here. And when we talked about the case when theta I plus theta t was 90 degrees, that's when our parallel became 0. This is where it's crossing on this graph. You can see our parallel had a value of about 0.2 for small incident angles, so nearly perpendicular to the surface, and then it can become 0 and then negative on the other when theta I becomes rather large, approaching pi over 2. And where it crosses, where this is 0, is when theta I plus theta t was 90 degrees. If you look on this graph or solve this numerically, this is when the Brewster angle is 0.983 radians or 56.3 degrees. And that's coming from this relation, which you may have seen already, that the tangent of the so-called Brewster angle is the ratio n2 over n1. Now just to emphasize where that's coming from, that's just coming from Snell's law. Right? So we had n1 sine theta I equals n2 sine theta t. And theta I, we can just let this equal the Brewster's angle that we're trying to solve for. Okay, so when the sum of theta I plus theta t is 90 degrees, that means this right side can be n2 sine, and here it would be then 90 degrees minus this Brewster angle or theta incident. Okay, but the sine of 90 degrees minus an angle is equal to the cosine of that original angle. So this would be n2 cos theta b. So what I see here is that if I divide everything by n1 and cos theta b, I can show that tangent of theta b is n2 over n1. Right? But now we have backed up quantitatively by going through the electromagnetic boundary conditions for waves reflecting off a boundary. We have worked out this relationship when the electric field is parallel to this plane of reflection. And we can see this relationship in this special angle called the Brewster's angle, which you can see on this graph here, which if you plug in, I put the point at 93 radians or 56.3 degrees, I forgot to mention, but that's for the case if N2 is 1.5 and N1 is 1, meaning you're in vacuum or air and you are reflecting off, say, some approximate value for glass, index of refraction. Forgot to mention that. This would clearly be different for different indices of refraction. Okay, so now we've understood where Brewster's angle is coming from. It's coming from electromagnetism, no surprise, and applying those boundary conditions. To finish up, we can discuss a bit about those other Fresnel equations. We just worked out one of them. And that was the case when the electric field was parallel to the reflection plane for Ki and Kr and Kt. But we can also have the other case when the electric field is perpendicular to that plane, so coming out of the screen toward you. And in that case, by E cross B pointing in the direction of the K vector, the wave direction, B would be pointing as shown in this bottom diagram. So that's the flip side. Now we solve for R parallel for the top case. Now it's this ratio of tangents. We did not solve, but we can just state here without proof that the reflection coefficient for the bottom case for the electric field, E0R over E0I, when the electric field is pointing out of the screen, is given by this ratio of sines, difference of sine theta I minus sine theta t over sine theta I plus sine theta t, with a minus sign that I'll come back to. Likewise, we could have also worked out for the transmitted waves, like the transmitted wave in the upper case for the electric field being in the plane of the reflection, all the electric fields basically. So here's an expression here, some sines and cosines, as well as the bottom case when electric field is perpendicular to that plane of the reflection but parallel to the surface. So it's this collection of sines and cosines as well. So that's the full set of Fresnel equations if we were to work them all out. We won't. We did one of them. And one thing to point out here is in the one case for R perpendicular, there is a negative sign that you can see there's here on let's look at the form on the far right side. Negative sine theta I minus sine theta t, sine theta I plus theta t. And what this is telling us is that it's flipping the sign of the reflected wave's amplitude relative to the incident wave's amplitude. And this will happen when N2 is greater than N1. If N2 is greater than N1, that implies that theta t is less than theta I. Right? If I go from a lower index of refraction, say in the upper side of the boundary, to a higher index refraction, the light wave will refract toward that perpendicular. So this theta t will be smaller than theta I. If theta t is smaller than theta I, then sine of that difference is a positive number. Sine of the sum is also going to be a positive number, so I have a negative out front. So my reflection coefficient has a negative sign in front, and what that means is that's equivalent to a 180 degree or pi radian phase shift for electromagnetic waves when they reflect off a material with a higher index of refraction. So if you're reflecting off material with a higher index of refraction, you're getting a 180 degree phase shift when doing so. It's like a string wave hitting a fixed boundary. So you have the wave and it's going to reflect off of the boundary. It might be a mount on the wall. The wave inverts. So here's the equivalent. The wave inverts, electromagnetic wave inverts when it goes off of a higher index of refraction material. So that's pretty interesting. You can see that coming from the math from solving for the Fresnel equations. Okay. So in general, though, so we've worked out, or at least discussed, all cases for the electric field polarization. We can consider reflections for both polarization directions. Let's just consider those by themselves. So R parallel is what we discussed initially, and then I introduced R perpendicular where you get that negative sign. And we can just plot the ratio of R parallel over R perpendicular versus the incident angle. Again, I can take the case where N1 is equal to 1 and N2 is 1.5, like going from air to glass. And I get this graph versus, again, this is versus theta I. And this is how that ratio looks. That ratio is not equal to 1, meaning the reflection ratio, the magnitude differs. So we have, less, say, of R parallel versus R perpendicular when I reflect. So once you reflect off of the surface between two dielectrics, you have now adjusted the polarization, or at least the reflection coefficient, put another way around, depends on the polarization. How much of it is, say, parallel to the reflection plane and how much is perpendicular, because that ratio is not a constant 1. And you can also see it's negative down here. You get that inverse for a certain range. Now, unpolarized light is light that's a collection of many, many waves where all polarizations are equally likely. So you have as much that are, say, parallel to the plane of reflection versus perpendicular to the plane of reflection. And what this is saying then is when unpolarized light reflects off of a surface, it will become partially and at a special angle fully polarized upon reflection. So you will, particularly in the case of the Brewster's angle, you're fully polarized. You've completely extinguished one of the components, that parallel component. That means all that's left from the reflected wave, ER, is the component that's perpendicular to the plane of the rays, this bottom case. This bottom case survives at the Brewster angle. The other case is extinguished. That's right here at this point where the ratio is 0. But even for other values, you can see there's still a changing amount. And so when you do extinguish one of the components of the polarization, you have just light that's either fully or partially polarized. You could extinguish that one more time if you had your Polaroid glasses, so polarized sunglasses, for example, and you can extinguish that final remaining polarization direction that survived after the reflection. All right, that ends this lecture. Hope that made some sense for you and understand where this polarization by reflection is coming from. We start from the laws of electromagnetism and the boundary conditions, and we'll end there.